Okay, so we've just been discussing the Poisson brackets, and well, let's just have a quick refresher. Remember what the Poisson brackets are used for. So we said we had Hamilton's equations, and let me just remind you, for a single particle, Hamilton's equation said that Q dot was equal to dh dp, and P dot was equal to minus dh dx. And then we said, let's imagine that we've got some observable on phase space. So it's a function of Q and P. And let's imagine that it doesn't depend explicitly on time. So all of its dependence on time is because it depends on Q and P depend on time. Well, if we wanted to calculate a time derivative of this quantity, this is going to be nothing but df dq times by q dot plus df dp times by p dot. And then we plug in Hamilton's equations. So this becomes df dq, and then q dot is dh dp. And now we're going to plug in p dot, which is negative. So I'm going to put the minus sign there already. We have got df dp, and then we've got dq. Okay, sorry. Shouldn't have written an x there, mixing up notations. So good, dq. But in this last expression here, you recognize we've got nothing but the Poisson bracket of f with h. So we would use the Poisson bracket to discuss the dynamics of the theory. So for a single particle, df dt would be the Poisson bracket of f with h. Then in the multi-particle picture where we had n particles, we might consider an observable f on the phase space that depends on all n positions qa and all n momenta pa. Well, performing an analysis very much like the one that I just wrote down, you can easily verify that the equation of motion in this n particle case is exactly the same. Df dt is equal to the Poisson bracket of f and h. And then in the field theory case, it's now natural to guess that, again, the equation of motion is exactly the same. Okay. So that's rather interesting that all of these equations of motion look exactly the same. And in fact, they are reflecting something that we know. So we just recently studied Newton's theorem. And one of the things that Newton's theorem told us was that for every conservation law, there is a conserved quantity. So if you were applying Newton, so Newton's theorem, one of the consequences and application of this shows that time translation invariance, so this is the symmetry that the laws of physics don't change in time. This means that energy is conserved. And as we said, this fact that time translation invariance implies energy is conserved, it's true in mechanics of one particle, mechanics of many particles, in field theory, in quantum mechanics, in quantum field theory. So it's a rather general statement. And that's what's going on. That's why this dynamical equation looks the same for the three theories. So why do I say that? Well, when you say energy is conserved, we know that energy is represented by the Hamiltonian. So the equation of motion that we want is d by dt of h is equal to 0. But now look at the equation of motion that we've got in all three cases above. Using that equation of motion, we would have the h dt is equal to the Poisson bracket of h with h. And in fact, if you just write out that Poisson bracket, it's obvious that this is 0. So all three equations look exactly the same because in all three, energy is conserved because of time translation invariance. Very good. Now, what was the other use of the Poisson brackets? So the nice thing is we could rewrite the entire theory just in terms of Poisson brackets, and that gave us the entire structure of the classical theory. And then we were able to quantize the theory by equating Poisson brackets to commutators. So, for example, in the single particle theory, the Poisson bracket of Q comma P is 1. What does this correspond to in the quantum theory? Well, if you work out the commutator between the operators, it's given by IH bar multiplied by the value of the Poisson bracket. This is lovely because this commutator between Q and P is an equation that determines what we mean by the position and momentum operators. So we're really finding a nice way to build the theory. We also get the dynamics because we've now written the dynamics in terms of a Poisson bracket. So the commutator of O with H would be IH bar times the Poisson bracket, and the Poisson bracket would just be the ODT. And that gives us the Heisenberg equation of motion. If we did this for the multi-particle system, well, I think that one of the things that you can very easily check is that the Poisson bracket between QA and PB is just delta AB. So that's an easy thing for you to check. So when we come to quantize the system, the commutator between position for H particle and momentum for the B particle is IH bar delta AB. And the dynamics of the theory is given by the same Heisenberg equation of motion. Now, of course, the Poisson bracket equations didn't change, so let's just outline those in blue. The dynamical equations written in the Poisson bracket was the same for one particle, n particles, or for fields. So we're going to find the same Heisenberg equation of motion in all three cases, because it's the Poisson bracket that we promote to be our equation of motion. Okay, now, for the fields, what do we get? Well, QA, that we would replace by, in fact, we wrote down this Poisson bracket just above. So let me just put it down here again. Phi of x comma t, phi of y comma t. X and y, because in the discrete case, I had A and B. And then the Kronecker delta is replaced by Dirac delta. So then in the quantum theory, we would have phi of x comma t with pi of y comma t would be equal to I delta of x minus y. Now this is great because this commutation relation will specify what I mean by my field operators. So I'd be able to solve that commutation relation to get hold of the field operators. And that's one of the things that we're going to do. And we're going to make sure that for the free field, we reproduce the answer that we got before. And then finally, again, promoting the Poisson bracket equation of motion, we get the equation of motion for our field theory. And again, it is just the Heisenberg equation of motion. Okay, let's keep going. Don't worry about the functional derivatives that appeared inside the Poisson bracket. We are going to return to that, and I'm going to define all of that carefully. Let's continue in a moment.